Hello again. It's the first time I've done two videos in 2 days. Sorry, I did your one for today or for Monday this morning, and I'm gonna do your one for Tuesday now. I will be traveling a little bit this week to Nashville. I have a race on Saturday, so that shouldn't affect anything. I should be able to get your videos and stuff to you, along with all the materials you'll need for class. But I just wanted to give you a heads up about that. I hope your quiz went well. That was just kind of to see if you were doing what I told you to do by looking over the rest of chapter 13.1. We're going to go over some of it today. Since you had that quiz, we might not get through all of 13.1. The way I have it set up, we should finish chapter 13 on Friday. So we'll go a little bit slower now, and then we'll get you ready next week for a test on chapter 13. But yeah, I hope your quiz went well. There were 2 points each. I gave Coach Reese the key. And yeah, I'm sure it was just pretty easy vocab and an equation in there every once in a while. Okay, so let's look and see if we can tell when objects sink or float. Let me erase this so I don't have to do it. We're just going to get through that and Archimedes' principle today, and get you to do a few practice problems, and that'll be it for the day. And yeah, we'll go from there. I heard that it was playoffs today, actually, or Monday. It's still Monday for me. So I hope that you all did well or are doing well. Thinking and praying for you guys. Okay, so let's look at 306. It says under sink or float. So what are the factors that act on an object that is placed in a fluid? So I think of a swimming pool or something like that. Yeah. One force is the upward force, or the buoyant force we just learned about, right? Of the liquid on the object, but there's also the downward force of the object's weight. So when something weighs in the water, it's going to push it down, right? The difference between the buoyant force and the object's weight determines whether the object sinks or floats, okay? So suppose you submerge 3 items in a tank filled with water. So think of it that way. I wish we were here because this would be a cool experiment to do. It would be pretty simple. So water has a density of 1 times 10 to the 3rd kilograms, okay, per meters cubed. They all have the same volume, 100 centimeters cubed, or 1.0 times 10 to the negative 4th meters cubed. One item is an ice cube with a mass of 0.09 kilograms. Okay, we're just setting up the experiment right here. The second is an aluminum can of soda with a 0.1 kilogram. With a mass of 0.1 kilogram. The third is a block of steel with a mass of 0.9 kilograms. How will each item move in the water? The upward force on all 3 objects, if you look at 3-7, it's all the same, okay? So the upward force, the buoyant force, is the same because all displace the same weight of water. Remember, it's not how heavy the object is, but how much water is displaced. That's the buoyant force, okay? The upward force can be calculated as shown. So F buoyant, let's see, the upward force on all 3 objects is the same. Okay, so to find this upward force, the buoyant force, you have the density of water times the volume times G. So the weight of the ice cube, F equals mg, is 0.88 newtons. So there's a net upward force and the ice cube will rise, okay? When it reaches the surface, there will still be a net upward force that will lift part of the ice cube out of the water. As a result, less water is going to be displaced, and the upward force will then be reduced because less water is going to be displaced, okay? The ice cube will float with just enough volume in the water so that the weight of the water displaced equals the weight of the ice cube. So an object will float because its density is less than the density of the fluid. So I told you earlier, that's how I would tell my nephew if something would float. If it has a density less than 1, then the object is going to float if it's in water, okay? The weight of the soda can is 0.98 newtons. The same mass as the So they're getting the 0.98 newtons, sorry, from Fg equals m times g. So what they're doing now, the weight of the soda can, if you go back up to it, has a mass of 0.1 kilograms. So you just multiply that times 9.8, and that's how they get the weight of the soda can, 9.8 newtons. Okay, so I don't want you to think that that's just coming out of nowhere. Okay, the weight of the soda can is 0.98 newtons, the same as the weight of the water displaced. Sorry. There is therefore no net force, and the can will remain wherever it's placed in the water at its neutral buoyancy, right? Because they're equal to each other. Sorry. Objects at neutral buoyancy are described as being weightless. This property is similar to that experienced by astronauts in orbit. This environment is simulated for astronauts when they train in swimming pools. Okay. The weight of the block of steel is 8.8 newtons, so they multiplied 9.8 times 0.9 kilograms, okay? And that's how they got that. Sorry. Still trying to get over this cold. It has a net downward force, so it will sink to the bottom of the tank. The net downward force is, its apparent weight is less than its real weight. All objects in a liquid, even those that sink, have an apparent weight that is less than when the object is in the air. So you can find the apparent weight by subtracting the mass, or from the buoyant force from the mass, Fg. As a result, the buoyant force of Archimedes' principal ships can be made of steel and still float as long as the hull is hollow and large enough so that the density of the ship is less than the density of water. Okay. You may have noticed that a ship loaded with cargo rides much lower in the water than a ship with an empty cargo hold. Submarines take advantage of Archimedes' principle as water is pumped in or out of a number of different chambers to change the submarine's net vertical force. So all of this, like when you think of boats, when you think of submarines, this all has to do with Archimedes' principle, okay? So it's pretty important. So the vertical net force will cause it to rise or sink if you change the vertical net force. Okay, Archimedes' principle also explains the buoyancy of fishes that have air bladders. The density of a fish is about the same as that of water. Fishes that have an air bladder can expand or contract the bladder. By expanding its air bladder, a fish can move upward in the water. The expansion displaces more water and increases its buoyant force. That makes sense now, right? The fish moves downward by contracting the volume of the air bladder. All right. Good. So now let's look at the example problem of Archimedes' principle. Hang on just a second. Okay. Let's move this here. All right, looking at Archimedes' principle. A cubic decimeter, 1.0 times 10 to the negative 3 meters cubed of aluminum is submerged in water. The density of aluminum is 2.7 times 10 to the third kilograms per meters cubed. What is the magnitude of the buoyant force acting on the metal? So we're going to look for the buoyant force, right? And then what is the apparent weight of the block? So we're looking for two things, the buoyant force and the apparent weight. Sorry, I have not cleaned this board since this morning, so it's a little dirty. So we're looking for the buoyant, and we're also looking for the apparent weight. I don't know what that was. Okay. So what do we know, though? We know the volume. 1.0 times 10 to the negative third meters cubed. All right, and we also know the density of aluminum. That's what that P looking thing is. is density, okay? So that's 2.7. This is just given to us in our problem. Times 10 to the third kilograms per meters cubed. All right, and the density of water. This is something that they probably won't tell you because they need to assume that you know it, okay? So it's 1.0. Times 10 to the third kilograms per meters cubed. Okay, that's just something you're going to have to know. All right, now that we have everything that we know, we need to calculate the buoyant force on the aluminum block. Okay, if you look over to page 306, you see how it was done with the example that we were given. Okay, so the buoyant force is equal to the density of water times times volume times G, okay? So, we just have to plug in, okay? All right, so now let's just plug in. So we have our density of water. Let's see. Hang on just a second. These are pretty easy problems. All right, so we have our density of water. That's what it asked for first, so that's 1.0 times 10 to the third kilograms per meters cubed. All right, and then we need to multiply that. Sorry, I wrote this kind of big, so it's going to look funny. By the volume of the aluminum. We're going to do that, then that's 1.0 times 10 to the negative third meters cubed times 9.8, because that's G, right? Meters per second squared. Okay, this looks really funny, but all of those three things are multiplied together, and that'll give you 9.8 newtons. Okay. So they're just on top of each other because I didn't have enough room. But those are just simply multiplied together. So when you're doing the buoyant force, you're using the density of the water, okay? All right. Now to find the apparent, which was the apparent weight, which was one of the questions on your quiz. To find the apparent weight, you have to have Fg minus the buoyant. So we found buoyant force, right? So now we just have to find the Fg and subtract the buoyant from that to get our apparent weight. Okay, so to do that, Fg, remember it's equal to mg, which is also equal to the density of the aluminum times the volume times G. Okay, so we have the density of the aluminum, right? It was given to us in our problem, 2.70 times 10 to the third kilograms per meters cubed times the volume, we're already given as well, 1.00, times 10 to the negative third meters cubed, times our handy dandy G, which is 9.8 meters per second squared. All right, and that will give us 2.65 or 26.5 newtons. Okay. Okay, and that's just finding our FG, okay? So we're not done yet. So we have to take this FG, which is 26.5. I'm just going to add it to the bottom, okay? FG is 26.5 newtons, and we found our buoyant, which is 9.8 newtons. Because remember, to find our apparent weight, it's FG minus the buoyant force, okay? So FG is 26.5 newtons minus 9.8 newtons. And that will give you 16.7 newtons for your apparent weight. So it's at the bottom, right here. Okay, good. So that's how we can use Archimedes' principle. All right, so I don't go over this enough, but make sure you check your answer. Are the units correct? The forces in apparent weight are in newtons as expected. Is the magnitude realistic? The buoyant force is about 1/3 the weight of the aluminum. It's sensible because the density of water is about 1/3 of that of aluminum, okay? Yeah, I wish that I could be there to do this floater sink this physics lab, because that one's a fun one. Okay, so let's see, this video is about 18 minutes right now. You did your quiz, that probably took about 10. Okay, so yes, you have time to do these practice problems today, so I'm going to let you do them in class. We'll do practice problems 6 and 7 on page 309. It'll be 5 points. I don't think I put that in the lesson plan, so Coach Reese, it'll be 5 points. I'll go over them tomorrow, and then we will finish the 13.1. We'll deal with fluids in motion and forces within liquids, and then we'll do that section 13.1 review, because that's more critical thinking, like I said. Yeah, so we'll do all of that on Wednesday, and then we'll start 13.2 on Thursday, and then, yeah, we will, yeah, finish 13.2 on Friday and get your study guide on Monday. Like I said, I hope you all did or do well on your playoffs today. I hope you guys win. I'm sure I'll hear from my sister. Yes, and I'm proud of the way you all are handling this year, like I always say. And you are so close to being done. So just push through, and you'll have a great summer before you have some significant changes in your life, which will be totally worth it. And yeah, just know that if you need anything, you can always reach out to me. Coach Reese has my email. I'm here for you all. So yeah, if you have any questions or just need somebody to talk to, let me know, and we can figure something out. All right, y'all have a good day. Bye.